Hi, welcome to this first lecture on bug advocacy. As we saw in the lectures on testing fundamentals, testing involves a broad range of activities. The common thread is empirical investigation. We're now going to consider how to most effectively report the results of that investigation. I've divided this work into 6 sections. There are a lot of slides. The black box software testing course is being used for experienced and junior practitioners, as well as for university and college students. The details in these slides are often more useful for practitioners who are actually trying to figure out how to write up problems under difficult circumstances. Students who have no testing experience might feel swamped by the level of detail. Don't try to memorize everything. You should be focusing on the main themes in terms of what you're studying for exams. As you go through projects where you're writing bug reports, come back and use the details for that. In terms of the main themes, I think the most important ones are these 4. First, effective bug reporting is a persuasive activity. Second, when you see the program fail, you should expect to do follow-up research in order to write an effective bug report. Third, there's a bug handling workflow. It involves a lot of people who make a lot of different decisions. Taken as a whole, it's a system, and the system puts out decisions that are made under uncertainty. That is, the best we can achieve are best guesses, well-informed guesses. And all decisions made under uncertainty are influenced by the decision maker's preferences and expectations. Finally, fourth, the care that you take in researching and writing your reports will impact your credibility, and that credibility will set expectations, and those expectations will drive your report's effectiveness. If you haven't already figured out how to adjust your media player so that it speeds up video lectures, this series of lectures would be a good time to run those experiments. I suggest that you do speed up your replay speed. Many people learn more when information comes at them a bit faster than a typical lecture. Here's the menu tree that I get from Windows Media Player, for example. It lets me adjust the speed to faster, which is what I recommend for Media Player. On other players, you can adjust the speed more precisely. Some people tell me that my voice is understandable to them even when speeded up by 2 times or slightly more. Now, the slides for this lecture don't contain all of the answers for the quizzes or the exams. A good set of slides conveys the lecture's structure, and it provides a bunch of details for later study, details that are too boring for me to speak and too boring for you to listen to, but that are still necessary for the material. No good lecture is constrained by its slides. In this case, the lecture actually runs about 25,000 words, and many of those are not in the slides. The most efficient way to work through this lecture is to print the slides in advance and make notes on the printouts. So let's start with the basics. We run experiments, we call those tests, to discover quality-related information about the product. We don't do our work in a vacuum. We do it because someone, our project stakeholders, need the information, and so they commission us to get it. For our work to be successful for them, we have to report that information back to them in a way that makes it useful for them. Making our reporting useful involves challenges, puzzles that will appear again and again in these lectures. First of these is the problem of time. How do we balance the time that we spend investigating a problem against the time that we need to look for new problems? Second is, how do we deal with the almost inevitable conflicts of interests among stakeholders? When people don't agree on what is a bug or what should be reported, what do we do? Third, even when there's no conflict of interest, pressures of time and expense and exhaustion create stress. How should we present problems to people who really wish they would just go away? Fourth, our effectiveness depends on our credibility. Credibility is something we can build over time and lose in an instant. What standard should we apply to our reporting to maintain our credibility? And fifth, we often face pressures to bury information or to shade it. Does a stakeholder ever have a right to say that we shouldn't report a classic problem because she's not interested in them? I actually think so. For example, imagine working very early in development with a programming team who want to understand if there's anything in their programming practices that are leading them to systematic mistakes. I think they have every right to say that they're completely uninterested in user interface problems and they don't want you to even waste their time on it. But does every stakeholder always have that right? Managing these puzzles goes to the core of our effectiveness in our work as testers. No matter how well a test group designs its tests, automates them, finds bugs, or documents our processes, our stakeholders don't get the value they need from our work if our bug reports are ineffective. To make this discussion understandable, it helps to refer to a bug workflow. A workflow is an ordered series of tasks that happen when you report a bug. In practice, bug workflows vary from company to company, so it follows as an abstraction. It's a simplified description of what's common, not necessarily what's standard. In our workflow, bug reporting starts when somebody finds a bug and writes a report. Usually that somebody is a tester. When someone reports a bug, the next task is to make sure it's an accurate report. This is especially common in open source projects like OpenOffice and Firefox, which allow anyone to report a bug. These bugs sit in the bug reporting system in an unconfirmed state until someone else verifies that they can follow the reporter's steps and get the bug as described. Often, the confirming tester adds a lot of critical details. Because of that, the programmers start on the bugs only after the bugs are confirmed. Now, this confirmation step very often takes more time and more expense than you might expect. And so in closed source projects, where most bug reporters are testers, most companies skip the confirmation step, at least for most bugs, instead relying on your competence as the tester to write up good bugs in the first place. In well-run companies, there is a deliberate process for deciding what bugs to fix, what to reject, and what to leave unfixed in the product. This process is called bug triage. In our workflow, the first person to look at the bug report is the programmer. The programmer starts by replicating the bug. That means doing what the report said in order to get the same result. The programmer then looks in the code to try to understand the cause. If the problem is easy enough to fix or serious enough, the programmer will probably just decide to fix it. And you don't need a lot of management attention for that. On the other hand, if the programmer thinks it's going to take a long time or doesn't think it's a serious enough bug or not a bug at all, then he passes it up to the change control board or the triage team who evaluate the programmer's rejection of the bug. Some companies put their trust for prioritization in management instead of in the individual programmers. And so the first person to look at every bug is either the entire triage team or the project manager. And then things get prioritized and assigned to individual programmers. This, I think, takes a lot more time, but it allows for centralized management control. In our workflow, the programmer sends a bug report to his manager if he thinks the bug shouldn't be fixed or if the fix is so costly that the manager should approve it. The project manager then decides whether the bug should be fixed, and if so, what's the priority. Priority means when should the bug be fixed. Some testers think they should prioritize the bugs because they think bugs should be fixed in order of severity. More serious bugs get fixed first. Well, certainly testers should assign severity, how serious the problem is, to the report. But I think priority is strictly a project manager's decision. Many of the factors involved in setting priority are completely invisible to the testers. As a very simple example, it is often much more efficient for a programmer to fix several related bugs in the same part of the program, the minor ones and the serious ones together, rather than fixing the serious ones this month and the minor ones next month, reopening the code and trying to figure out over and over again what this part of the code does. When the programmer and project manager decide not to fix a bug, it goes to the triage team. The triage team has the authority to tell the project manager to fix a bug. Sometimes they'll override the project manager, especially if it looks as though the project manager didn't understand the significance of the problem. But not every bug report will or should result in a code change. For example, there's room for honest, thoughtful disagreement about the product's design. The team might consider our concerns and decide they like the product better like it is. As another example, a lot of reports involve compatibility with peripheral devices, like printers or video cards. If a problem only shows up with a few outdated printers, the most cost-effective and most reasonable thing to do might be to give a refund to the few customers who have the old equipment and tell everybody basically don't use it with that machine. In other cases, there really is a problem, but the risk and the cost to fix that problem is so high that this just isn't going to get fixed or not fixed in this release. All of the approvals for those rejections come through the triage team. The triage team serves as an appeal process, a forum for considering whether a particular decision to not fix something is sound. So the next step in our workflow comes when the programmer fixes the bug and sends it back to you. You have to do some retesting. You have to ask whether the bug was fixed and also whether the fix might have introduced some other problems. In terms of whether the bug is fixed, occasionally you'll actually get code that comes back that doesn't fix the problem. The programmer misunderstood the report and fixed something else, or else send you back the wrong code. More often what happens is that the programmer misunderstands the scope of the problem and gives you something that actually fixes the narrow description of the bug. If you do exactly your steps in your bug report, you don't see the problem anymore. But if you change the steps slightly, or if you change the data, the failure comes back. Another variation on that theme, in this part of the program, you see the program misbehaves, but the program does similar things in other places. And the programmer fixes the problem here, but doesn't notice that they could have made the mistake elsewhere. When you retest, you discover that that happens. Now, the problem of side effects is different. Side effects happen when you actually fix this bug, but you break something else in the process. When we say that code is unmaintainable, what we mean is that the code is so hard to understand, or its pieces are so tightly intertwined, that unexpected side effects are very likely. Back when people were trying to fix really old programs to cope with the year 2000 bugs, some programming teams had side effect rates of over 200%. That is to say, for every fix they made, they added 2 new bugs. These companies, or at least the ones that I watched in this situation, eventually had to abandon their old software, buying entirely new hardware and new software to run their business under a new process. Deciding what types of tests to run to check for side effects of a fix is not always straightforward. You could try to test everything, but you'll run out of time. There are glass box techniques, such as program slicing, that help programmers who have access to the source code try to decide whether parts of the code might be affected by a change to this part, and thus what other parts of the program should be checked. But as a black box tester, you don't have access to the source code. You can't do program slicing, and so your retests are going to be based on your intuition about relationships in the program, and your intuition is going to evolve over time. Here's the final slide on the workflow. When the project manager decides not to fix a bug, the triage team serves as an appeal board, and anyone on the project can argue to the triage team that this bug should be fixed. One of the most serious mistakes that many testers make is to appeal too many times. They try to get every bug fixed. You put your credibility on the line every time you appeal a rejected bug. If you don't have a strong argument, every time, people will learn to tune you out. They will decide you are wasting their time. If the project manager read this report and wasn't convinced by it, the appeal will probably fail unless you can show that the problem is more serious, more likely to show up in normal use, or more annoying to a stakeholder with influence than was evident in the initial report. To do that, you will probably have to do more research, and that will take time. Most project managers' decisions about bug deferrals are reasonable and are treated as reasonable by the triage team. If I can't improve my report, genuinely, persuasively improve it, I rarely make the appeal. So now we've completed the overview of how bugs get handled start to finish. Let's take a look at what makes bug reports effective. A bug report is a request. It's a request from the tester to the programmer to add a new task to her work list. Near the end of the project, when most black box testing happens and when most bugs get fixed, programmers have way too much to do. They're tired, they're working overtime. If a bug looks unimportant or too complicated, the programmers will ignore it. And that's not because the programmers don't care about quality. It's because they can't get everything done. They don't have time to thoroughly investigate a bug if it looks like they're not going to fix it anyway. People notice how well researched and how carefully worded your bug reports are. You'll get a reputation based on your bug reports. People you've never met, sometimes including managers who have a say in what kind of raise you get, will read your reports and form impressions of you based on those reports. The most creative, thorough testing in the world won't help your reputation if your bug reports don't reflect your intelligence and your care. When you write a bug report, you're not just reporting a set of observations. You're trying to get someone to do something. That's the point of writing most reports, to get the bugs fixed. So in practice, this means that sometimes you're going to have to investigate the bug in more detail or take greater care with the wording than you might think is the most efficient use of your time, because that extra time is what's needed to help convince the person who has to do the extra work that it really needs to be done. To develop the theme of persuasive writing of bug reports, it's useful to have some shared terminology. So I'm going to spend the rest of today's lecture looking at definitions, starting with the definition of the word bug. What's a bug? I usually ask this question as a pre-lecture exercise, either an in-class brainstorming session or in an online discussion. The purpose of the exercise is to help students see a variety of ideas about what makes a product effective. In industry, there are a lot of incompatible definitions of the word bug. This variability causes a lot of communication problems, primarily among people who aren't expecting that there's this variability. It's very important to understand because there are many different definitions. It's pointless to talk about the one true definition of this term. I'm not going to persuade someone else, if they've got a long experience, that their definition is the wrong definition. And they're not going to persuade me, most of the time, that my definition is the wrong definition. The more useful thing to do is to try to understand what the other person means when they use the word and what's useful about their definition. Then you can talk to them using the word their way, and they can talk to you understanding what you mean by the word, and we can have effective communication. So let's consider the exercise. When I ask for a definition of a software error, individual students give 2, 3, 4 definitions. Across the class, we get a variety. Here's a list that's drawn from several classes. Let's consider a few of these. The first one, which some people are very firmly attached to, is that the only valid type of bug is a non-conformance, a deviation from a specification. Well, sure, if there is a detailed specification and the program doesn't do what it says, then something's wrong with the program or with the specification or with both. But suppose your group creates a word processor that can't print. This is a failing product. Word processors have to print, whether the specification for that word processor mentions printing or not. Most specifications are incomplete. That doesn't stop bad behavior from being a bug. We cannot restrict our idea of bug reporting to products with thorough specifications. Many best-selling products, including products that I consider best in class, were not developed from detailed specifications. Another restriction that some people like is that all genuine bugs are coding errors. A coding error causes the program to behave in ways that the programmer didn't intend. But there are also design errors. The program behaves the way the programmer intended, but we don't like it. If a feature that should be easy to use is hard and complex, people won't use it. I've seen reports that talk about abandonment rates of products, people giving up on using software that was developed for them, as high as 50% of those abandonments being blamed on difficult design, not on errors in the code. So coding errors is just part of the problem. The field's classic definition is not restricted to specifications or coding errors. It's from Glenn Myers. A bug is a failure to meet the reasonable expectations of a user. This is good as far as it goes, but which user? All of them? Different users use the product in different ways for different purposes. And so a problem that's important for one of them doesn't matter, or is even a feature for someone else. So how do we resolve that conflict? Which user's expectations are reasonable? This is often a source of serious disagreement among development teams. Another issue that I have with Myers' definition is his restriction to the reasonable expectations of a user. I want to think more broadly about stakeholders. A stakeholder is someone with a vested interest in the product, somebody who's affected by the success or the failure of the product. A stakeholder with influence is somebody that the product development team is going to pay attention to and try to please. Think about the vice president of sales for a product that's going to be sold. If the vice president says, I don't like this feature, it's going to make it hard to sell, does it matter if the vice president is a user? The definition that I personally prefer is the one in the box. A bug is any unnecessary or unreasonable reduction in the quality of the product. This gets to the heart of what I think a bug report is all about. We report a bug, no matter whether it's a coding error or a specification error or anything, we report a bug because we think that if the program fixed it, it would be a better program. Several other words come up when we talk about bugs. For example, fault and failure and defect are common words. What's the difference between these? Let's use a simple example to create a context. Imagine we have a program that adds 2 numbers. So you enter a number at the keyboard, it stores it in variable A. You enter another number in the keyboard, it stores it in variable B. Then it divides A by B, and everything works fine, unless you enter a 0 into B, in which case crash, divide by 0. The failure is the crash with the divide by zero error message. The underlying fault, the error in the code, is that there's no error checking for divide by zero. There's a critical condition, a critical test for this failure, and that's putting a 0 into variable b. If you use any other number, you're not going to get the crash. You're not going to see the bug. As to the word defect, I don't see a defect here, so I wouldn't report one. But I'll come back to the word defect in a few slides. The IEEE publishes a standard glossary of software engineering terms. There are many different definitions for the word error. They list 4 of them, and their list incorporates ideas of fault and failure. Here are the IEEE definitions of fault and failure. The fault is the mistake in the code. The failure is the misbehavior caused by the fault. In this course, we use basically the IEEE definition for failure. It's the misbehavior of the program. As far as fault or error, I use those 2 words interchangeably. If I'm looking at a coding error, then the definition is just like the IEEE definition. The fault is the mistake you can look at in the code. But there are other kinds of errors that we recognize as bugs. Anything that makes the program unsatisfactory is a bug. And whatever the root cause of that unsatisfactoriness is, that's the fault or the underlying error. In bug reporting, one of the essential ideas is that there are conditions that cause a failure. In a bug report, we list the conditions required to produce the failure. Well, one of the critical challenges of effective bug reporting is boiling down a complex test to a short list of the critical conditions. Those few things that you absolutely need to know to be able to reproduce the bug. The simpler the description, as long as it's accurate and sufficient for reproducing the bug, the easier it is to understand, and the more efficient the troubleshooting for that bug is probably going to be. Now, sometimes a program fails gradually. It shows a few small problems at first that you may or may not notice, but then eventually it works up to something really serious, like a crash or data corruption. The serious failures are often hard to reproduce because the underlying problem is really building up over time. Spotting symptoms, the early warning signals that a more serious failure is on its way, is a critical skill for making very many bugs reproducible. Let's look at the word defect. Some people, especially some consultants who don't have to live with the consequences of their advice, insist that we should call all bugs defects. Let me speak as a lawyer who has some trial experience. I think it is usually a big mistake to use the word defect. The problem is that companies get sued for problems caused by their software. The burden is on the person who brings the suit, the plaintiff, to prove that the software is defective. If the plaintiff can't make their case, the company is not liable. The legal standards associated with the legal term defect can be a lot narrower than your standards or mine for reporting a bug. But if the plaintiff's lawyers get to say, even the defendant's own quality assurance experts call this a defect, your company's lawyer is going to find it really hard. Some consultants smile about this and say, look, a company should lose its lawsuits if its software is defective, according to their definition of the word defect. So they say reporting a bug as a defect is the honest and professional thing to do. And as consultants, what we're bound to do is the honest and professional thing, and to heck with the consequences. Occasionally, that's probably the right thing to do. Let me give you an example. I tested a product that had a compatibility bug that could actually destroy a specific kind of printer in a way that created a fire hazard. Now, the programmer said that the real problem was that the printer's manufacturer's design was bad. Well, after a long argument where they just insisted that they would not change the code, it was the printer manufacturer's fault, I finally wrote a bug report that said that the product was dangerously defective, that it could result in a fire, and the fire might kill somebody. I then called the company's lawyer, and I read the report to him word for word. Well, in this particular case, the lawyer thanked me and got the bug fixed right away. In this particular case, I was willing to risk infuriating the project manager and drawing the lawyer's attention to me by writing a legal conclusion into my bug report. If you're ready to call your company's lawyer about a bug, by all means, write the word defect into your product report and then call the lawyer. But if you aren't ready to make this level of fuss about a bug, don't write your report in a way that might increase your company's risk of a lawsuit later. Own your word. There are lots of other words that you can honestly and ethically use that don't involve litigation. If you hate the word bug, call it an anomaly, or an incident, or a problem. Just don't call it a defect. That brings us back to our opening question. What's a bug? A bug is an aspect of the product that causes an unnecessary or unreasonable reduction in the quality of the product. This includes design weaknesses, documentation errors, usability annoyances, anything that unnecessarily reduces quality. So what's this emphasis on unnecessary reduction? What I'm trying to point out is that some aspects of a product limit its quality but aren't bugs. Let me use a simple example. Under American car safety standards, if you drive your car into a wall at 5 miles an hour or less, it's not supposed to damage the car or hurt the driver. If you drive at 10 miles an hour and you get a ding on the car, that's too bad. The limit is 5 miles an hour. Is that a bug? Well, on the one hand, you could say, well, there's a standard, there's a regulation. If it meets the regulation, it's fine. But what if I told you that we knew how to make cars that could withstand 40-mile-an-hour collision into a brick wall, that you could buy one today? Wouldn't that make the 5-mile-an-hour limit look unrealistically low quality? So here's one of these cars. Of course, they're a little expensive. And for the consumer version, you'd probably have to take off the turret and the machine guns, except maybe in Texas. But people are still buying Toyotas. They could buy these, but instead they buy cars that have much less collision safety. Why is that? Because these are ridiculously expensive. And at some point, cost becomes prohibitive. At some point, people would rather have designed-in limitations that they understand and agree to than spend lots more money for an extra level of quality that maybe they don't even want. That kind of limitation is not a bug. So if we're going to define a bug in terms of lowered quality, then we need a definition of quality. You might wonder why I'm spending all this time on definitions. If I'm making the statement in every bug report that the program's quality is low in a particular way, then thinking about quality helps me decide what extra information to look for, what details to emphasize, so that I can write a report that even if somebody disagrees with it, they can at least say, oh, okay, well, I understand why he calls this a bug. Phil Crosby's probably best known for his book Quality is Free. In his definition, conformance with requirements is very widely quoted. But it's important not to misunderstand him. He is often oversimplified. The word conformance does mean adherence to a specification or a standard. But when Crosby talks about conforming to requirements, he's talking about the user's actual requirements, not necessarily what's written down in a requirements specification document. The specification, like all written specifications, might be useful, but all specs are incomplete and error-prone. Now, some students of mine at this point protest because they do contract-based software development, and the contract includes detailed requirements. Their task is to deliver a product that satisfies the contract, and that's what they do. So isn't that quality? Shouldn't their quality control efforts be focused on making sure that the product conforms to the contract? Well, if you have a contractual specification, of course it's important to deliver a product that meets the spec. Otherwise, you don't get paid. Of course, it's important to test the product against the spec. But it can be very hard to specify everything you actually need. Kaoru Ishikawa makes this point really well in his book on Japanese quality control. The example he used involved the challenges of specifying the quality of paper that goes through printing presses, huge rolls of paper. And what's the strength of the paper? How do we specify that the paper shouldn't rip? You'd think that should be very easy to precisely specify, but he demonstrates that it's actually much more complex than it seems. All too often, you can deliver a product that satisfies a specific set of specifications, but that doesn't satisfy the customer's actual underlying needs. Now, meeting the contract means the customer has to pay you for it. That's important. But if the product doesn't work well for that customer, it's not high quality. Not for that customer, no matter what the requirement document said, and no matter how much they paid you for it. Quality is not conformance to the document. It's conformance to the needs. Joseph Juran added a useful refinement to the idea of quality. His most widely quoted definition is fitness for use, and again, that's oversimplified. He elaborated on this by distinguishing between satisfiers and dissatisfiers. Think about a computer game that you like and would recommend to a friend. What makes it so good? Anything that makes you like the game more is a satisfier. Anything that makes you like the game less is a dissatisfier. The ideal product has lots of satisfiers and not many dissatisfiers. Fitness for use is not just about unfitness for use and the lack of unfitnesses, it's also about fitnesses, satisfiers. Some people, like marketing folks, focus intensely on satisfiers. Other people, like testers, focus more on dissatisfiers, which we write up in bug reports. But when we think about quality, both perspectives are important. This distinction between satisfiers and dissatisfiers opens up a broader discussion of the dimensions of quality. For example, reliability means how long the program can run without failing. High reliability means not very many dissatisfiers of the oops, it failed kind. But capability, what the program can do for you, what the benefits are that it provides, that's a pretty important aspect of quality too. People abandon products because it doesn't deliver the benefits that they need, not just because it fails all the time. Another thing that thinking about satisfiers and dissatisfiers leads us to is the recognition that different members of the software development team are going to be more in tune with different aspects of what makes a product great. For example, a technical writer might pay more attention to design inconsistencies that confuse users and make the product harder to write about, learn about, and understand, whereas a programmer might pay much more attention to the internal excellence of the code. Good code is fast, compact, easy to understand by another programmer, easy to modify. Books like Martin Fowler's classic, Refactoring, are all about the quality of code, and they don't speak at all to the ease of using the program, to inconsistencies of the kind that a tech writer would notice. There's a pretty common dynamic in software development meetings between someone who comes in and says, we have to have this new feature. We just have to have it. It's much more important than fixing this bug. And then someone else who says, oh, no, you have to fix this bug. Don't you have any sense of quality? Well, the person who's trying to add a satisfier might be every bit as committed to the quality of the product as the person who's trying to take away a dissatisfier. Keeping this diversity in mind can help you speak respectfully to somebody who makes a quality-related statement that might otherwise sound foolish to you. Keeping their perspective in mind can help you negotiate with them way more effectively. Jerry Weinberg captured this diversity really well when he said quality is value to some person. And that's the definition we're going to adopt in this course. Different people value different things. So something that's a big problem for one stakeholder might seem trivial to another. The idea of value is very important. The way to convince someone that something is a bug is to help them understand how it threatens the value of that product. If not for them, then for someone else. Applying Weinberg's definition of quality, we can add a little precision to our definition of the word bug. A bug is an attribute of a software product that reduces its value to a favored stakeholder or increases its value to a disfavored stakeholder without a sufficiently large countervailing benefit. Countervailing benefit, that's like the tank example. The countervailing benefit there is tanks are way too expensive, cars are cheaper. In terms of stakeholders, some fast definitions. A stakeholder is someone who is affected by the success or failure of the product. A stakeholder with influence is somebody that the development team pays attention to. They want to satisfy this person. A disfavored stakeholder is someone the product is designed to dissatisfy. For example, security features in a product are designed to dissatisfy attackers who are trying to access the data in the product. James Bach and Michael Bolton present an abbreviated version of this definition, which is a bug is something that threatens the value of the product. Now, the important abbreviation is that value of the product is always value of the product to someone. Some cases, disfavored stakeholders, the threat is that the value will be too high instead of too low. So let's sum up. Quality is value to some person. It's subjective. The value of the same thing differs from person to person. A bug report exposes something that reduces the product's value to some stakeholder. Sometimes everyone agrees that what you're reporting is a bug, but other times what you find might be important to only one stakeholder. You should still report that bug. But if you realize that's the situation, your most effective report will be the one that gives this person the information in the way that's going to be the most useful for them to come back to the project team and say, This is why you need to pay attention to it.